Hey, hello everybody. Looks like I just got my second question for, this semester and for this chapter. And I better stop counting because I probably will lose track. But it's number 11 from chapter 15. And let's work through this one here. It says a half a kilogram object is attached to a spring with a force constant of 8 newtons per meter, vibrates in simple harmonic motion with an amplitude of 10 centimeters. Now, I must say that the author could have done a better job here because the author didn't say whether or not the spring was vertical or the spring was horizontal. The author also didn't say whether the object, started, if it's horizontal, at equilibrium and moved out and around, or if it started at its maximum to the right or maximum to the left and was let go. So I think because of that, and as I scan the problems, A, B, and C, the questions that are asked, it doesn't matter whether the spring is vertical, horizontal, or whether it starts at equilibrium or starts at its maximum or starts at its minimum. So I suppose it was unnecessary for the author to say that. And maybe that was even part of the problem. However, it does bring up this whole idea, and as we look at the springs, if you remember, we add up all the forces, and if it was only horizontal, it would be minus kx. If it was vertical and we added up all the forces, well, then we would have that minus mg, but we would also have a minus kx, but the x would be made up of a little piece to equilibrium plus a little bit more, and the little piece to equilibrium and gravity would cancel off, and you would still get this minus kx. It's just your x kind of has a different meaning. Here on a vertical spring, the x means from the new equilibrium when you're hanging it because it stretches the spring, whereas x just means from the natural length of the spring. So there is a little difference between the horizontal and vertical spring, but the bottom line is it does just come down to a minus kx, whether it's a horizontal spring or a vertical spring. And maybe I should have put horizontal and vertical. And the reason that's relevant is because when you add up all the forces and they equal that and you set it equal to ma, and remember a then is the second derivative of position. This will give me a chance to kind of review the lecture. But if you wanted to kind of know the simple answer to what's involved in this chapter, there it is. What's involved in this chapter is to sit down and look at your mechanics. So take your Physics 121 and then write out your forces or your torques, depending if it's a translation or a rotational problem. And when we do that, if we ever end up with something that has a minus and some constants and then the function again, the solution to that, when you take a derivative of that function twice and get the same function back with a negative and the thing out in front, is that the solution is some amplitude and then cosine of, and it would oscillate back to the fourth, and the prefactor would be the square root of whatever's out in front here. So the negative sign, ignore that, and the function itself, ignore that. But this is the omega. And, of course, there might be some starting phase, and that was my comment earlier, that he didn't really say whether it started in the middle or to the left or left to the right, but this would be the general solution. So I don't think you need to do any of this kind of steps to actually do this problem. This is the kind of thing that coming into the problem, the author kind of assumes you already know. I'm just using this as an opportunity to maybe let you see it again and hopefully let it sink in a little bit more because it takes a while. But anyways, knowing that this would then be the solution, we can actually answer, I think, the easier of the questions. A, what is the maximum value of the speed and the acceleration? because when you take the derivative of this, so velocity, you would get the amplitude. And when you take a derivative of a cosine, you would get a... Ooh, let me pause for a moment. Yeah, because I just flashed over to the solutions, and I see your the person who did the solution did something kind of interesting. They put in a value really for here. They decided that, I guess, that it didn't matter. And since it didn't matter, they go, well, we'll just make our own. That could be a little misleading, but nonetheless, maybe I'll follow suit. It certainly makes things a lot easier. As I look at the solution here, for whatever reason, the person doing the solution said, well, let's just say it started in the middle and moved out. So a graph of it would be this. It starts at 0 and moves to the right, so it goes positive. So it should be a sine function. So that means this should be cosine square root of k over mt and a shift of pi over 2. And in fact, the person doing the solution just even said, oh, don't even write it like a cosine. That if you're going to shift it over, you might as well write it like a sine. And so go sine of the square root of k over mt and without a phase. And that's why I say it's easier to work with if you don't have that phase. And my guess is that the individual doing the solution probably did that because as I look at problem C, the C, or part C of it, says moving, it says, what is the time required to move from 0, so the origin, over to 8? So I think they're just going to say, well, okay, let's start at 0 and move to a position of 8. The amplitude is 10, and so they're going to move to a position of 8. And so we might as well think about it starting at time equals to 0 at the center. All right, so I got to admit, it sure makes the problem a little bit easier not having to deal with this phase. So I'll follow along with that. And maybe the first thing to do is actually to calculate the square root of k over m, which we call the omega. Because they, let's see, they gave us the k, what was it up here, at 8. And they gave us the mass as 1/2. So 8 divided by half is 16. Square root of 16 is a 4. So if we do that, we can write the equation for position as an amplitude of 10. And we can write it as a sine of 4t. And there's no, as I just commented, there's no phase to worry about. And we can put a value here, and we can do a sine instead of a cosine. But like I said, take that with a little flexibility, because it doesn't have to be a sine here. It could, all these questions would give you the same answer, whether you did a sine or a cosine. In fact, we could have done cosine with no phase and made the math a little bit easier that way too. That would have been like thinking of it starting here. So it's like somebody pulls the spring and then lets it go, and so it goes back to 0 first and then to negative and back and forth like a cosine function does, because a cosine function does that. It starts at its maximum and goes down to 0 and then to negative and so forth and so on. So, again, I could have been just as comfortable calling it a cosine with no phase, or cosine and just leave this as a general variable. We don't know what it is. That's maybe a little harder because math-wise we have it there, but it's probably a little more accurate in the amount of information we have. But I'm going to follow along with what the solution did, and the author, again, for reasons that I think are going to be a little more obvious in part C, said, all right, let's do this. Let's call it a sine function. All right. So now I can get back to where I was, which was A, and A says what's the velocity and I believe also acceleration. Now I need to read it again. Now maximum value of its speed and its acceleration. So you take the derivative. And so the derivative, it's got a 10 out in front, it's got a sine of 4t. So when you take the derivative, the 10 comes out in front. The derivative of a sine is a cosine, and then don't forget the chain rule, so there's a 4. So this becomes a 40 cosine 4t for the equation for the velocity. And of course, then to get its maximum, the maximum is that value out in front, because you know the cosine function goes up and down between a +1 and a -1. So 40 would be equal to the maximum speed. And I think I mentioned this in the first video solution. The author actually works this out for you in symbols and says this would be A times omega. And of course, he got that by doing what I just did. So you can just kind of memorize this or kind of repeat. I kind of like just repeating it because then I don't have to memorize a bunch of stuff. If I memorize a bunch of stuff, I just forget it. But I know I can just take the position function and take its derivative. So the amplitude would be 10. The omega, as we said, was 4. And then we would get the 40. So either way, we're going to get the 40. Oh, and I should point out we're working with distance in centimeters and time in seconds. So it would be 40 centimeters per second for the maximum speed. And if you took the derivative yet again, you would get the equation for the acceleration. So I'll just pull the 40 out in front. The derivative of a cosine function is a negative sine function. And then the chain rule pulls out another 4. So this becomes 160, and I guess there's a negative, and then there's a sine of 4t. And again, since the problem is looking for the maximum, the number out in front is the maximum, because this sine function, as time goes on, is always going to vary between a +1 and a -1. And so when the sine of 4t is a -1, multiplied by that -1, you'd get 160. So this would be 160, and again, the units would be centimeter per second squared. So there would be your maximum acceleration. And again, your author did this in symbols in the book, and I think I might even have done it in the lecture in symbols, but he got the A times omega squared, which A is the 10, the omega is the 4, and we'll square it. The 4 squared 16 times 10 is 160. So sure enough, you can just memorize this and do a plug and chug, or look it up and do a plug and chug. But I'm not a big fan of plugging and chug. So this is where it comes from, and so I just kind of want to work through it. It also makes a nice review of Physics 121 and says, okay, this is how you get velocity. This is how you get acceleration. So those would be your maximum values. Now, let's go on to B. Let's see if I need to get another page here or fit it in. But I think B is a little bit harder. It says the speed and the acceleration of the object when it is 6 centimeters from equilibrium. This is a really good one. Again, it's a nice review of Physics 121, because if I were to take an object and drop it, and I were to say, all right, what is the speed of it after it has fallen, say, 3 meters? You really have two choices for this. One choice is to figure how much time does it take to fall the 3 meters. So in other words, get the time. And then once you get the time, you can then figure out its speed, because you know the acceleration is g times the acceleration times time would be the speed, I guess, plus initial speed. But I said drop it, so that's a 0. And it makes it kind of a two-step process, so that you use position. So I'll say you start with position, position leads to time, time then leads to speed. And there's nothing wrong with that approach. It's just two steps. And it's the kind of thing we learned first in Physics 121. But we also then, after doing all these acceleration stuff in chapters 5 and 6, when we got into chapters 7 and 8 and we got into energy, we said what was really nice is we use position and go right to velocity using the principles of energy. And so that would be my suggestion here, that we don't use the acceleration approach. And again, not that it's wrong, it's just kind of two steps. You got to use position to get time, to get velocity. I read this and I see right away that they're asking about position and velocity, and so in my mind, what's triggering in my mind is the whole conservation of energy approach to our mechanics, not acceleration and forces approach. In fact, I've got myself curious now. I'm going to flip over to the solutions here. What did he do for B? Oh yeah, so B, the author here does this. The author then works out the time by taking the inverse sine of it. And then once he's got the time, comes back up to what we did up here and puts it in there for the velocity approach. Which, again, it's not bad, it's not hard, but it kind of blows past the energy. So I'm going to use the energy. This time I'm not going to stick to the way the author does it. I know I jumped on board with the sine function instead of the cosine function, mostly because they're really the same to me, but also because I'm looking at part C later on, where a sine function would make it a little easier to handle than a cosine function. So I'm glad I looked, and I like what he did with the sine function, but I will tell you, I don't like what he did. I don't dislike it either. Like I said, this is fine approach. It's just a little too naive. It kind of, I think, shortchanges you of the more advanced energy approach. You're going back to chapters 4 and 5, and that's a little more elementary than chapters 7 and 8. So this is a one-step process and a little more advanced. So I'm gonna do the energy approach and encourage you to do the energy approach here. Okay, so for B, we can do conservation of energy, and the total energy equals the potential energy plus the kinetic energy. And so if I just kind of draw a little object as it's going back and forth, back and forth, back and forth, at some point along this back and forth, it will have a certain amount of potential energy from the stretched spring. So there's the 1/2 kx squared from our chapters 7 and 8 in Physics 121. And then at that particular point also, it would be moving, so it would have a kinetic energy. So that must be its total energy. Now, you could also say, instead of a general spot, you could say, well, right in the center part, the x is 0, and it only has a kinetic energy. Okay, so these two, which would maybe be the energy at some arbitrary point, must be equal to this, which would be its energy, which would all be kinetic when it's at its equilibrium point. But you could also say this. You could also say when it gets all the way to its maximum displacement, that is at its amplitude, it would all be potential, and it would come to a stop, so it has no kinetic energy. So you could also say this totals 1/2 k a squared. And so all of those work fine. And in fact, I think I'll take advantage of that and write 1/2 k a squared is equal to 1/2 k x squared plus 1/2 mv squared. And then, of course, there's a half in each term, so I can get rid of that. And now you'll see I have an equation that gives me velocity as a function of position. And that is what I was trying to say to remind you of your Physics 121, that that's the beauty of energy. There's a direct connection between position and velocity. It's a one-step connection. Whereas doing it the way your author did, it's more of your acceleration and forces. You have to use position and do a, an inverse trig function to get time, and then use that time to get velocity. So it's a two-step process. But like I said, each of them are equally valid. All right. So I'm going to then write this then as k(a) squared minus kx squared equals to mv squared. Maybe I'll even move the m to the other side. And get v squared. And then maybe I'll even factor out k over m, and this equation was also worked out by your author. So you could look it up and just kind of plug and chug and get the velocity. But I'll go ahead and then put in the numbers. The k over m is the omega squared. That's the 4 squared, or a 16, or 8 divided by a half. So maybe I'll just put 8 over a half. The amplitude, let me double check here. What was a 10, right? Amplitude's 10. And then I'll put a square. And then so we want to find when the object is 6 centimeters from the equilibrium. So 6 squared is 36. Well, maybe I should have just wrote 6 squared. And that equals to v squared. So this is a 16, what is this? 100 minus a 36, v squared. 16, what is 100 minus 36? Isn't that 64? And so now when I take the square root of the 16 is a 4. The square root of the 64 is an 8, and so that makes a 32. Awesome. All right, and of course we're working with centimeters and seconds for our time. So I should get a speed of 32 centimeters per second for B. Now, there's another part to this. It says, what is the acceleration? And I'll say the same thing. Just like here, we could do something like this. We know its position. Its position could lead to time. And if we know time, we can get acceleration, because that is exactly what we had in this equation right here. We have the acceleration as a function of time. But it begs the question, is there a one-step process? Can we go from position right to acceleration? And I think so, because position is related to force. This is the magnitude of the force. This is the Hooke's law. I didn't put the minus in there. And then a force divided by mass is the acceleration. So I kind of like this approach. It's, again, the direct approach between acceleration and, in this case, force and position. And we never have to mess with figuring out what the time is. And so we don't have to do the inverse trig function. Not that an inverse trig function is that hard. But let me switch over to the answer. I bet the author does. Oh, yeah, well, and it would make sense by this one. He's already done the inverse trig function for the time here, and so now he's just going to plug it in there. So by the time you already did this, yeah, this would be a better approach, because you don't have to solve for time again once you've already done that. But I want to do this one, just maybe to be a little different and let you see it a different way. But that's also what popped into my mind first, is not, to do it this way, but to mess with it this way here. Okay, so I guess I need a little more space here. So this F over M is the A, the F is the Kx. And then, of course, this K over M is the omega squared, but I'll write it as 8 over 0.5. Careful here. I might need to be a little careful with my units here, though. Let me watch my units. This is newtons per meter. And this would be kilograms. And this position then would be 0.06 meters. That's 6 centimeters. Yeah, so maybe this isn't a better approach. I really got to watch my units here. Let me just do the numbers here first. This 8 divided by the 4 is the 16, and the 0.06. I'll worry about that. But see, this Newton per meter, that's why I wanted that meter there to cancel that. Then I would have the Newton over a kilogram, and a Newton is a kilogram meter per second squared, so that's going to give me meters per second. Oh, actually, that would have been fine because there's a meter in there that would have canceled, and I could have done that and finished with centimeters. So, all right, so I guess I didn't need to be real careful there with the units, but I'm glad nonetheless I went through it. So this is 16 times 0.06, which comes out to be 0.96 meters per second squared, or if you like, 96 centimeters per second squared for the acceleration. Oh, now also, that's the magnitude of it. Just kind of dawned on me. Are they asking for the maximum, or are they asking at the same time? Let me explain that difference here. It says be the speed and the acceleration of the object when it's at 6. From the equilibrium. Now, if we're going back and forth, let's imagine it's starting at 0 and it's going to go to an amplitude of 10. And so it goes out, if it's at 6 right here, it's moving in a positive direction. So I put 32, but remember, this is a square root, so it's actually plus or minus. So the author should be a little more clear here, because it could go 6, can come out, and on the way back it could be at 6. And so really the velocity should be plus or minus 32. It could be going to the right, or it could be going to the left. Let's see, let me just make sure it says, it doesn't give me any information. It says the speed and the acceleration when the object is 6 centimeters from the equilibrium. So the solutions in the author's book here just lead a positive 32. So that's implying that it is heading towards the right. And of course, the spring is pulling it to the left. So the corresponding positive 32 centimeters per second goes with the corresponding negative 96 centimeters per second squared. But on the other hand, if it's gone out to its maximum and come back and it's going this way to the left, then its velocity would be a negative 32. And of course, its acceleration would still be that way. So it would be a negative pulling it that way. So it's always getting pulled that way. So I guess it's always a negative. But the speed could actually be positive or negative. It doesn't really, I don't think there's enough information to really say whether it's heading on out to its maximum amplitude, or if it's already been there and it's heading on back. So I didn't see anything. Let me scan again that would make me indicate which it is. It just says B, the speed and the acceleration of when the object is 6 centimeters from the equilibrium. All right. Let me, so I would have to say that I don't think the solution was as complete as it could be. It really should be a plus or minus 32. But this is always a negative 96 at that point. Yeah. And the spring's always pulling it to the left. Okay, and then finally we get to the last one, the one that, like I said, I think maybe is a little bit why the author picked the sine function. So C says the time interval required for the object to move from 0 to 8. Now let me write down the equation for position again. And here is the equation using the sine. Because we want to know when it goes from x equaling 0 out to x equaling 8. So what we would need to do is to solve for what time is it when it is at position 0. And then what time is it, so I'll call that time 1 and time 2. What time is it when it's at position 8? And as I said earlier, way back at the beginning, we could have used the sine or the cosine function. And I started with just kind of the general one. But what's nice is right here, if you then put in x equals to 0, and solve for time, of course you would divide both sides by 10 and you'd get 0 equals to sine of 4t. Then you would take the inverse sign, which would say 4t has to equal 0 or t has to equal 0. And sure enough, the sine function is saying at time equals to 0, it's at its equilibrium. Well, exactly, right? We know that that's true for a sine function. A sine function starts at time equals to 0, it starts at 0, exactly. So the advantage of doing the sine one is I don't think you have to actually do this mathematics. You don't have to figure out the moment in time when it is at position 0. That was just so obvious. But I thought I'd go through the math. The one that takes a little bit of math is the inverse trig function here. And by the way, I should point out that I successfully avoided doing an inverse trig function when in part B, where I did it by energy instead of doing it by time and acceleration. But they're directly asking for time, so I've got to do the trig function, and then I've got to do the math of an inverse trig function. Again, not that it's hard. I'm not trying to avoid it. It's just that's, I didn't do an inverse trig function until this step. Okay, so now what I'm going to do is I'm going to put, let's put in this equation. So I've got the 8, and I've got the 10, and I've got the sine of 4t. So when I bring this over, that's a 0.8 equals to sine of 4t. And when I take the inverse sine of both sides, so let me turn on my calculator and check and make sure I'm in radians, okay? Because look, we're doing real numbers right here, so I got to be in radians. So taking the inverse sine of 0.8, this would be 0.9, I'll call it 27. And of course, the inverse sine of a sine is inverse operators. So divide by 4, and I get 0.232 seconds. And let me jump to the solutions. I don't think there's any other way to do it other than that. Yeah. And so technically subtract these two, this minus 0, but that was the advantage of the sine function. I didn't have to really solve it. I don't have to subtract. I just can finish it right there. All right, and I think that was it. Let me jump back over to the question. It was just a C, right? Yeah, C. All right. Hope that helped.